introduction to whole numbers. Familiarizing yourself with the whole numbers, with numbers themselves, is the very first step to doing anything in math. You can't even learn operations without knowing numbers. And as you may know, math is the branch of science that deals specifically with numbers. And how, then you can get into physics, try to apply these numbers to the real world or to interpret the real world as numbers or apply terms, etc. But again, the very first step before we get anywhere is to learn numbers. So in this lesson, we want to be able to do this list. First off, we're going to start with the I can statement. So basically, I can graph the numbers on the number line, order the whole numbers, use expanded notation, round whole numbers, and read and interpret tables and graphs. First off, let's learn about sets. A set is a collection of objects. If the set is finite, we can describe the set completely by listing all the objects in the set and enclosing the list in curly braces. Now, finite means there's a certain amount. Okay, so for example, the set S equals open curly brace, dog, comma, cat, comma, parakeet, close curly brace, is the set whose members are dog, cat, and parakeet. But say that a set is infinite, then we need to be more clever with our description. So take, for example, the set of natural numbers, or as you may call them, the counting numbers. This set is n equals, open curly brace, 1, 2, 3, 4, 5, dot, 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 then close curly brace. Now, because this set is infinite, or, there are an infinite number of natural numbers, we obviously can't list all of them. So we're just going to list a few. We listed 1, 2, 3, 4, and 5, and then we added those 3 dots. Those 3 dots essentially mean etc., or so on, or to be continued, or there are more, or but wait, there's more. Now, if you understand the natural numbers, if you understand 1, 2, 3, 4, 5, so on, right? What are the whole numbers? Well, we simply add a 0 in front of the 1 to make the set of whole numbers. W, so natural numbers, is listed by n, W equals, in our curly braces, 0, 1, 2, 3, 4, and then 5, and so on. Now, let's learn how to graph them. Let's meet our first objective. It is a simple matter to set up a correspondence between the whole numbers and points on a number line. Now, that was a nasty paragraph to just read, or a nasty sentence. It's a correspondence between whole numbers, blah, blah, blah. Let's make this simple. It's a simple matter to draw a line, add tick marks, and write our numbers. Watch this. The first step, we're going to draw a line, then set a tick mark at 0. Right? Notice how I drew my line. I have my very first tick mark, or that little dash. It's going vertical. It's perpendicular to my line. Right? I place a 0 above it. Now declare unit length. Now, obviously, this isn't exact, but you can tell that all my tick marks are relatively the same distance from each other. Then, the remainder of the whole numbers now fall easily in place on the number line. Now, consecutively, I have 0, then the next tick mark I have 1, and then 2, and then 3, and then 4, and so on. So an example, right? When asked to graph a whole number in a number line, shade in a solid dot position on the number line that corresponds to the given whole number. So, I'm asked to graph 1, 3, and 5 on my number line. So, on the ticks 1, 3, and 5, I'm going to put a circle on those ticks. I'm going to color them in, okay? Just as you can tell. Now, I want you to try. Just pause the video, grab a piece of paper, and a pencil and I want you to draw your number line. I want you to try to graph 3, 4, and 6. Once you've done so and you've finished the problem, your solution should look like my graph, but on 3, 4, and 6, you should have dots. Okay. Now, suppose that A and B are whole numbers located on the number line so that the point representing the whole number A lies to the left of the point representing the whole number B. Then the whole number A is less than the whole number B, and right, A is less than B. Alternatively, we can also say that the whole number B is greater than the whole number A, and right, B is greater than A. What does any of that mean, though? Well, we have a correspondence between the whole numbers and points on the number line, and we can order the whole numbers in a natural way. Note that as you move to the left along the number line, the numbers get smaller. As you move to the right, the numbers get bigger. Okay, so this makes sense. All we're doing is saying whether A is bigger or smaller to B. That's all we're saying. So if A is on the left side, right, it's smaller because B is on the right side. And as I go to the left, I get smaller. As I go to the right, I get bigger. So in the first part, I'm going to say A is less than B. Because if I have, I don't know, let's say A is 2 and B is 5. If I have 2 cookies, and I have, my friend Tim has 5 cookies, well, I have less cookies than Tim, right? 2 is less than 5. Now, I could also say that 5 is greater than 2. So B is greater than 2, or B is greater than A. It makes sense, right? So this is our comparison property. When comparing two whole numbers, A and B, only one of the 3 possibilities is true. A is less than B, or A equals B, or A is greater than B. You cannot have more than one. You can only have one of these. If A is equal to B, then it's impossible to have A less than or greater than B. So let's just try a new example, or another example. We want to compare whole numbers, right? So we're going to compare the whole numbers 25 and 31. I can have 2 solutions, right? On the number line, 25 is located to the left of 31. Therefore, 25 is less than 31, and we would write 25, use our less than sign, 31. Or, we can easily say that 31 is greater than 25. So now I want you to try. Compare the whole numbers 18 and 12. What you should have gotten was that 18 is greater than 12, or that 12 is less than 18. Okay, now this is fun. Okay, we want to learn how to use expanded notation. So the whole numbers, D equals 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now notice there's no dot dot dot. This is a finite set. Okay, this set is called the digits. Okay, and this set is used to construct larger whole numbers. For example, consider the whole number 222. Okay, it is made up of 3 2's, but the position of each 2 describes a different meaning or value. The first 2 is in the hundreds position and represents 2 hundreds, or 200. The second 2 is in the tens position and represents 2 tens, or 20. And the third 2 is in the ones position and represents 2 ones, or 2. So, you can look at our little table here. 2 is in the hundreds column, 2 is in the tens column, and 2 is in the ones column, right? Now, here's a cool trick that we can do. This hundreds column is 100. This tens column is 110, and this ones column is 1. Simply multiply the number above it, and then as a quantity, add it all. So 2 times 100 is 200. 2 times 10 is 20. 2 times 1 is 2. Now add those. 200 plus 20 plus 2 equals 222. This is our cool trick we're going to use, right? So, continued. Consider the larger number 123,456,789. Now the following table shows the place value of each digit. In expanded notation, we would write 100 million plus 2 10 millions plus 3 millions plus 400 thousands plus 5 ten thousands plus 6 thousands plus 7 hundreds plus 8 tens plus 9 ones. Whoa. Why don't we just read it like this, right? 123,456,789, like I said the first time. Okay, but in expanded notation, we have to write 100 million plus 210, etc. Basically, written out in expanded notation is just the written out version of this table. But we're going to use this table right now because it's a lot easier to visually see and to kind of comprehend. Now we're also going to use our multiplication and addition trick again. So take 1 times 100 millions, or 100 million, take 2 times 10 million, take 3 times 1 million, take 4 times 100,000, take 5 times 10,000, take 6 times 1,000, take 7 times 100, take 8 times 10, and take 9 times 1, and add them all together. So an example, write the number 23,712 in expanded notation, then pronounce the result. Okay, well let's write it in expanded notation first. So in expanded notation, I would write 2 10,000s plus 3 thousands plus 7 hundreds plus 1 10 plus 2 ones. And notice how I start. Okay, notice how I start on my right. These I'm going to start on my right and work my way to the left. The 2's in the 1 spot, and it goes 1s, 10s, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions, 100 millions, and so on. So, that's how I know where my numbers lie. My 2 lies on the 1s. My 1 lies on the 10s. My 7 lies in the hundreds. My 3 lies in the thousands. And my 2 lies in the 10,000s. And this is pronounced 23,712. Now I want you to try, okay? Write the number 54,615 in expanded notation, and then pronounce the result. What you should have got was 5 10,000s, 4 thousands, 6 hundreds, 1 tens, and 5 ones. And when you pronounced it, you should have said 54,615. Let's try again. Write the number 203,405 in expanded notation, then pronounce the result. Well, in expanded notation, 203,405 becomes 200 thousands plus 0 10 thousands plus 3 thousands plus 4 hundreds plus 0 tens plus 5 ones. Since 0 10 thousands is 0 and 0 tens is also 0, this can also be written as 200 thousands plus 3 thousands plus 4 hundreds plus 5 ones. This is pronounced 203,405. Wow, that's a lot. But now, I want you to try though. Write the number 430, 705 in expanded notation, and then I want you to pronounce the result. What you should have got was 400 thousands, 30 thousands, or 3 10 thousands, my bad, and then 0 10 thousands, 7 hundreds, 0 tens, 5 ones. Now, in expanded notation, you could have said 400 thousands plus 3 10 thousands plus 7 hundreds plus 5 ones, right? Because you have no tens and you have no thousands. And then when you pronounced it, you should have said 430,705. Okay, we're almost done. The mathematical notation. Okay, this little equal sign, but it's kind of curly, it's kind of wiggly. It means approximately equal to. Not quite there. It doesn't quite equal said or given value, but it approximately equals it. It's almost there. Okay, and we're going to be using that symbol for this, right? So when less precision is needed, we round numbers to a particular place. For example, suppose a store owner needs approximately 87 boxes of 10 penny nails, but they can only be ordered in cartons containing 10 boxes. Note that 87 is located closer to 9 tens, or 90. That it is to 8 tens, or 80. Thus, rounded to the nearest 10, 87 is approximately equal to 90. The store owner decides that 90 boxes is probably a better fit to his need. Okay, now on the other hand, the same store owner estimates that he will need 230 bags of peat moss, whatever that is, for his garden section. Note that 230 is closer to 200s than it is to 300s. The store owner worries that he might have overestimated his needs, so he rounds down to the nearest hundred. So 230 is approximately equal to 200. Alright? Rules for rounding. To round a number to a particular place, follow these steps. Mark the place you wish to round. 2. This is called the rounding digit. Now check the next digit to the right of your digit marked in step 1. This is called your test digit. If it's greater than 5 or equal to 5, we're going to take your rounding digit and add 1, and then forget about everything else. If it's less than 5, we're going to leave your rounding digit the same, and leave everything else. So, round the number 8,769 to the nearest tens. Alright, well, mark the rounding number in test digits. Okay, well, we're going to mark it. 6 is in the tens place, so I'm going to make that my rounding digit. Now I need to use the digit that's to the right, that's adjacent to it. So 9, the ones place, is my test digit. Okay, so the test digit is greater than 5, right? 9 is greater than 5. So the rules of rounding require that we add 1 to the rounding digit and then make all digits to the right of the rounding digit zeros, thus rounded to the nearest 10. 8,769 is approximately equal to 8,770. So, very last, right? Don't need to do anything after this. We're going to reading data in graphical form is an important skill. The data in table 1.1, as you can see to the left, provides measures of carbon dioxide content in the atmosphere, gathered in the month of January at the observatory atop Mauna Loa in Hawaii. Okay? Now let's look at these two graphs. In figure 1.1a, a bar graph is used to display the carbon dioxide measurements. The year the measurement was taken is placed on the horizontal axis, and the height of each bar equals the amount of carbon dioxide in the atmosphere during that year. So this is a bar graph. We're going to use bars to represent what we're trying to say. So in 1965, alright, this is the year that we're measuring. Okay, 1965, it went all the way up to somewhere between 300 and 400. Now it's closer to 300 though. I'm going to say it was probably 310, right? So 310. I remember this. It's parts per million, right? So parts per million, 300 parts per million is about 310. Okay. Now in 1.1b, we're using a line graph. Okay, a line graph is used to display the carbon dioxide measurements. Again, the dates of measurement are placed on the horizontal axis, and the amount of carbon dioxide in the atmosphere is placed on the vertical axis. Instead of using the height of a bar to represent the carbon dioxide measurement, we place a dot at a height that represents the carbon monoxide content, or carbon dioxide. Once each data point is plotted, we connect consecutive data points with line segments. So again, in 1965, I'm going to go up and place my dot where it was measured. So 310. Then 1975, I'm going to place the dot there. And then I'm going to connect my dots with lines. And that's where we get line graph from.